So let's start thinking about how to go build a memory coherence protocol. So as a little bit of a warm-up, for our memory coherence protocol, we'll actually see that this problem exists beyond multiprocessor systems. So a lot of the motivation for these ideas of memory coherence protocols actually predate even having multiprocessors. And how is that possible? Well, the same problem ends up in I/O. So let's say you have parallel I/O. So let's take a look at this picture here. We have one processor, a uniprocessor system, and we have main memory here, and we have a cache. And then over here, we have a disk with a DMA engine. So a direct memory access engine. So this is a autonomous controller here which can move data from the disk to main memory and vice versa. So how does this come up with something like parallel? What problems can come up with something like parallel I/O? Well, let's say that the disk here wants to transfer a page from the disk to physical memory or to main memory while the processor is running. Well, you program up the DMA controller and says, go. Well, it's going to start copying data here from the disk out to main memory. Well, because we have not done anything on this bus, we just use it as a way to communicate, the cache here might have the same addresses that are being written to. And now they're going to have a stale value. So they'll never actually pick up the value from that just got DMA'd or just got moved from the disk to physical memory. Likewise, so that's disk to memory. You might get stale data in the cache. Likewise, you could have memory trying to go to disk here. So let's say you start to have a DMA transfer from main memory to disk, but you might have data in the cache here. Let's say it's a write back cache. Well, this transfer could get started, but it could miss updated data here in the cache. So it could try to start doing copies, but because we said the DMA engine just copies directly from physical memory to disk, it'll just miss those updates. So there's no good way for the processor to go and write data to the disk. And this is something you fundamentally want to do. So there's a couple of solutions to this. And this is sort of a brain teaser to get you thinking about this. But what do you need to do to guarantee some way of having the disk here, for instance, be able to see the data that's in the cache? Well, how do you go about doing this? You need some way to either invalidate the cache and send these to main memory and have the disk pull out the updated or most up-to-date copies. And this is a sort of similar notion as what we have to do back in this example here. We need some way to either get the most up-to-date value or invalidate or kick data out of a particular cache in order to allow the new reader of the data to be able to see updates. And this is sort of an introduction to where we're going to go, which is cache coherence protocols. And cache coherence protocols are going to give us some guarantees and give us mechanisms in order to actually see that data that has been updated that would otherwise be stale, according to some rules. OK. Other things going on here. I think that's basically the basis of this. But I wanted to just get across the idea here that you might need cache coherence protocols even in a single processor system. And it gets even more complex in a multiprocessor system. So what was one of the big solutions to this problem? Let's say you wanted to have caches. You wanted to be able to have either parallel I/O going on or multiple processors with caches be able to access data, and you want a write to one processor to be able to be seen by another processor, or the write from one processor to a cache be able to be seen by the disk controller here. And fundamentally, the problem here is this DMA engine only knows to go to main memory. It doesn't know that there might be dirty data in the cache for the same address.